Hello everyone, welcome back. In this tutorial, I'm going to teach you the explanation of the full Python scripts for data preparations and visualization. Here is a detailed step-by-step explanation of your code, tailored to help the beginners understand data analyst workflow with Spark and Pandas. Before you start to begin, here is the easy to understand explanation of this code. I'm going to start by the click code. And the first one is I'm going to load data from the specific file path into the Spark data frame's name. This code reads the data from a CSV, separate value file into the Spark data frames, which is a distributed data structure used for processing large data set. This is tell Spark that you want to read a CSV file. The Spark read object is the entry points for reading data. The other explanation is to the info schema is first. Do not automatically detect the data type for each column, which means all data will be read as strings unless you specify types later. Second option is indicates that the CSV has no header row, no columns names in this first row, so Spark will treat all rows as a data, and columns will be named under score C1 and C1, 2, 3. Next Python code is option separator with a comma. It is specified the separator used in the CSV file, in this case, a comma. Finally, we are going to definite of the data frames with load function, which is load the data from the specified file path into a Spark data frames named df. So this code loads as a CSV file into Spark with the specific options inference, and so all data is read as a strings, no header row, so columns are names on the C1, C0 or 1 extra, and then the comma separated. You will need additional steps to rename columns and convert data types as needs for analysis. Next step is I'm going to retrieve the first row of the Spark data frames df. The result is a row object containing all value of this first row. This column name is to obtain all list of the column header label as a strings that can be used to rename the data frames columns. How does it use? Iterates over each cell the first row and converts it to a string and add it to a list named columns name. So this retrieves its first row of data, which is actually header. It converts each header cell into a string and stores all headers in a list called columns name. So this list will be used later to rename columns of the data frames for easier analysis. This source code filters functions is to keeps only a row that satisfies a condition. df dot this one is the Spark data frame loaded from a CSV without headers. Its columns are automatically named underscore C01 extra. So df dot underscore C0 refers to the first column. This source is the very first row of your data frames, which contain the header, was stored earlier as a first row. So first row 0 is the value of the first cell in that headers row. This conditions is to keep only those rows where the first column's value does not equal the header's value. This efficiently removes the header row from the data. Do you know why is that necessary? When a CSV lacked a header, the first row contains column names, not actually data. we need to remove this header row from the data analysis. So the data is clean. The next step is I'm going to this method rename and then column names, and there's an effect. To df, this method is renames the columns of the Spark data frame. Star column's name is the asterisk is used to unpack the list column's name into individual column names arguments. Previously, you extracted the actual headers from the first row and store them as a list of string. Here is the effect that the data frames df underscore no underscore headers, which had default columns names like underscore C0 or C1. The extra now has the correct meaningful columns names assigned. Do you know why is this necessary? Based on the knowledge whether using proper columns names make data analysis much easier and more readable. So this allows you to access columns like release year, IMDb score, extra, instead of underscore C0, underscore C1. This is one of the summary rename all columns in the data frames to the real headers extracted earlier. And another one is it is using unpacking operator start to pass the lists as individual arguments. Next is PDF and equal df with the columns to pandas. These pandas make it easier to do their analysis and plotting with many Python's visualization library like Seaborn's matplot library. Another source code is to convert IMDb underscore the columns to numeric, the floats with errors. The entry that is an invalid entry like a string or missing data are converted to none. Why is used it? It is to ensure IMDb score is a number, so statistical calculations and plots work properly. This one is IMDb with this column. We're going to convert the IMDb columns to integer or float to accurately analyze the correlations with numbers of votes and to enable numerical operations. This is a convert to import column and handle invalid data gracefully with the error code. Prepare data for further analysis or visualizations. With the printing, it display all districts unique the value present into the type, the columns of your pandas data frame. It is useful for understanding what category or labels are present, especially if the data is messy. Why is this helpful? It is to verify what values are stored in type, like movie and show, series, TV, or misspelling the entry. It is to decide whether you need to clean, standardize, or filters the data based on those values. This code is for standardize the specified value, suppose after cleaning. These functions categorize and standardize different label variations in your type column into commands catalog like movie, show, and other. This is a handle missing value, the none, by assigning other. The converts all entries to lowercase string to ensure case insensitive matching. From this, if the string contains movie, and classify it as a movie, and if string contains show or series, and classify as show. If TV appears, clarify as show, and final line is anything else gets labels the other. With this code, this line is applies the normalized type function to each label, each value in the type column of the pandas data frames. This is on purpose to re-categorize and standardize all entities so that regardless of how they were originally labeled or misspelling, they are grouped into consistent category like movie and show or others. In raw data, categories might be inconsistent, misspelled, or have extra words. So this is a line transform the type column into the consistent categories. It helps keep your analysis clean and meaningful. So this line is ensure a type is a string, and it converts the type column to string type. So string operations work reliably. The make all text lowercase is convert all characters in the type in lowercase. The remove is going to stripes any white space at the start or end of each string value. For example, movies, there is space between. It becomes the movie without any space in this word. So this is why we're using this standardizing and reboot analyst. These two lines set up categories bins to group movie and show based on their runtime. So define the edge of each runtime interval like 30, and later in this code we use those kind of PD cut and label. The string label assigned to each interval, making the data more readable and easier to analyze visually. Why use the bins is to group numerical data into a meaningful category, the 0 to 30 minutes instead of lots of separate value. Also, it is to identify the patterns or traits across the category like average scores or counts. So this is a line to convert all value into the runtimes columns of your pandas data frames PDF to numeric type such as float. The arguments, the errors equal course is means if any value cannot be converted to a number, for example text missing data, it will be replaced with none, which is not a number, which indicates missing or invalid data. This is why the importance to ensure the proper numerical operations. Later, to calculate, the calculations require runtime to be numbers, not strings. To handle mass data is to sometimes data have invalid or inconsistent entry. This converts valid values to numbers and marks invalid ones as missing. In this line is to remove all rows in your data frames PDF where the runtime value is not missing or invalid data. This is important. It is important to ensure data quality and prepare data for accurate insights. Ensure this cleans your data set by removing movie and show with unknown or robust runtime data and making subsequent analysis trustworthy. In this line is to filter your data frames to keep only row where runtime is. So over more than 0 and less than 300. This filter your data frames is to greater than or 0 minutes to exclude 0 or negative values, less than 300 minutes to excessively long or unrealistic runtime. This is what we used is to very useful to remove outliers or unrealistic data and ensure data relevance. Is to focus only on typical movie or show durations, making your results more meaningful. In these lines with pd.cut, the function is the segments is the runtimes value into interval based on your specified bins. So this is 3 parameters like bins and label and write. the bins is bin, label is labels, right and false. These parameters is the edge of each interval, like 0, 36. So labels is the human readable label, like 0, 30-6, etc. This is last, the parameter is first. These intervals are left inclusive, like start to end, and meaning the left edges is included but the right is not. So once you get the results, is to create a new columns runtime underscore bin, is where each movie and show falls into the runtime category, like 0-3, 30-6, etc. This is why useful is to categorize continuous data and facilitates the comparison. Since you get the previous Python code, we can count how many movies shows fall into the each runtimes underscore bins category. Is to display the frequencies, number of entries for each the runtime interval, like 0-30 and 30-6 until over 240. Is to inspect the data distributions across your categories and help you understand how many movie shows are in each runtime range, useful for validating your binning. Now it's time to using this line to calculate the average IMDb score per runtime bin. This group lined data frames PDF by each runtime bin category, such as this one for this one, and calculates the mean the IMDb score within each runtime category. Another one is reset the index with reset the index library is to the results. That is, results is on clean data frames within column, runtime bin, and IMDb score. It tells you how IMDb score vary for move and show of different duration range. For example, you might find the certain runtime group tends to have a higher or lower range, and providing insights into viewers' preference. In this line is to keep only move and show. It filters your pandas data frames to keep only row, whereas the type column is the movie or show. It executes entries like series, to documentary, and others. This is very useful. You might want to focus your analysis or visualizations on just movies and shows to keep it simple and relevant. Also, this is helpful in cleaning their data and removing categories that might not be of interest. So these operations ensure your data sets contain only primary contents types, movie and show, and providing clarity and focus for your analysis. So now is the process with the plotting and or to analyze with the standardization's specific value. This block of the code creates a bubble scatterplot showing the relationship between runtime and IMDb score with additional information like both and type, with a figure size setup, and printing columns creates a bubble scatterplot with axis and size color, title and labels, as well as the customizations, grid and legends, and show the plot. This visualization helps identify outliers or interesting patterns and relation between movie length and rate. Finally, this is how popularity IMDb votes vary with sites. Okay, would you like to prepare these explanations with by clicking this run cell? It might be error. This area is not defined, so this line doesn't necessary. I'm going to remove this and click the run cell again. So this is the results with the visualizations. So in summary, for you, in this the output value we can get the type. The values are diverse, and standardizing help in the better grouping. Another one is most movies are around 90 to the 120 minutes. The dataset contains over 1,500 entries in these most common durations groups, with very few in the very long category. You might know what columns are available for further analysis or visualizations. Now I want to break down what this output tells us step by step, so you can understand it clearly. The first one is unique value in type column. This type columns contains various categories like movie and show and striped series, and some messy entry or typos. So this is the insight. The data is inconsistent, so you need to standardize those labels before analysis, which you are already done with your normalization function. Second is durations of the runtime bin. Here, with movie duration group, it tells us how many movie shows fall into each duration group. Most movies are in the 90 and 112 minutes range, around the 1695 entries. Next, most commons are 30 to 60 minutes, around 1087 entries, and 60 and 90 minutes. There are very few long movies, like 210 minutes, and none over 240 minutes. It is the implications that we can say the typical movie's length is between 60 and 120 minutes, consistent with standard features film. The third one is columns in the data frames. This one. In this output, we can know that there are all columns headers, have the numeric number, ID, and title, types label, description, release years, and age certifications, scribes or database ID, and both and your runtime category. So you can now confidently refer to those columns for analyze. And now, here is the explanation of what the bubble chart reveals about the data. Is suitable for teaching you. What does the bubble chart tell us? Here's a focus on relationship. It's between movie and show, runtimes, and viewer IMDb score with an additional dimension, the number of votes. This key insight from the chart. First one is distribution of the range across the runtime. We think about that. It is most data points are scattered in the middle runtime range, like 60 to 150 minutes. Longer movies like 180 and 200 minutes are fewer but tends to have higher IMDb score, mini bubble higher on the y-axis. And short movies between 0 to 30 minutes are also present, but show more variability in IMDb scores, including some lower rates. Second is pattern of the ranges. Movie show with average IMDb score 7 are spread across different runtimes, but there's a tendency for longer movies over 150 minutes to have more higher rates bubble. The very short movies under 30 minutes tend to have more lower ratings, possibly due to many being less popular or experimental. The third one is bubble size. As number of the votes, the larger bubbles, more votes appear to mostly around moderate to higher range, around 6 to 8. This indicates that more popular movies or show with lots of vote tend to have higher IMDb score. The fewer higher rate movies have few votes, a smaller bubble, suggesting niche or less viewed content. We info longer movies above the 150 minutes might tend to, but not always, have better ratings, possibly because epic or well-produced movies attract more votes and higher scores. The most popular contents aligns with the higher rating, indicating that well-rated movies also tend to more popular. The shorter movies, less than 30 minutes, are more valuable. In summary, these charts help us to understand how runtimes relate to viewer rating and popularity. It suggests longer and higher quality movies often receive higher score and more votes. There are a wide variety of rating across the runtime, but patterns emerging when looking at large datasets. Thank you for watching this